Okay, cool. And with that, I'll hand it over to you, Avishek.
Uh, Thank you, Pratna. Thank you, everybody, for joining in. Uh, I really appreciate everybody coming in. I'm sure everybody's busy, so bringing out some time and attending our event. It means a lot to us. So thank you all for joining in. Today, I wanted to give a bit of like a technical talk around Apache Druid. I've been working with Apache Druid for the past few months at work on a project. So basically, I have had the opportunity to go a little bit deep into a storage system, which I was interested in previously, but I mostly used it as a black box, right? As a software engineer, you call your storage APIs, you run SQL, but you don't really peek under the hood and see how a storage system is actually designed, or at least I didn't. It was a great opportunity for me to dig a little bit deeper into how a storage system is actually architected. And I'm very excited to learn. I was very excited to learn all of these concepts and how it's designed, and wanted to share it with you as well. So thank you for coming in. Let's get started. So a brief agenda for today. First, I'm going to be introducing Druid, and then we're going to be talking a little bit about the use cases that Druid is designed for, and some of the key design features that it uses to fulfill those use cases. So I really want you to understand the relationship between the design features and the use cases that is like a bit of symbiotic relationship on those two attributes. And then we'll also go a little bit deeper into the architecture of the storage system. And then I'm gonna do a ingestion and a data querying demo. And then we'll end up with a summary and brief discussion. So that's the agenda for today. We have a lot to cover, so let me just get started right away. So what is Apache Druid? Apache Druid is an open source distributed database built in Java designed for OLAP queries on large data sets. Now I know that's a mouthful and has so many different like terminologies. So let me actually break it down. Open source. Apache Druid is an open source technology, which means that the code is completely public, and anybody can go ahead and use it, fork it, fix their own bugs. It's a distributed database. So what does that mean? That means that it's deployed in clusters. It can be deployed in clusters of like just one node to hundreds of nodes, hundreds to thousands of nodes. And you'll see in the architecture section of the talk as well. Even the database itself has many different subcomponents that will make the database. And those are all systems, independent systems, and they interact via the network. So it's pretty much designed as a distributed systems as well. And it's built in Java, which I was very excited in because I first learned programming learning Java. So just the fact that, hey, like the language that I know best is used to build such a complex storage system was quite interesting to me. And then it's designed for OLAP queries. So let me give you a little bit of a description on what an OLAP query type is versus what an OLTP query type might be. So OLAP, as it's written there, it stands for online analytical processing. So it's query use cases that is heavy for analytical purposes, right? Whereas OLTP, which stands for online transactions processing, is more on like individual transaction basis. So let me give you an example. Let's say we have a e-commerce website and a user is going in and creating an order, right? So what normally happens is a new row is inserted in the orders database, right? And then that order is, so that's OLTP, where your transaction is being created into the database. So the effect is only on one particular row or a handful of rows. Whereas, let me give you an example of OLAP, where a product analyst wants to know which products sold most in the last couple of months, right? So that kind of query is not limited to one row. It's scanning like all rows across the past couple of months, and then maybe the product analyst wants to do slice and dice of data in sense of like hey, let me group that by the product type, and then maybe let's sort by, let me sort by the amount that got sold. So all of these slicing and dicing is like more of like analytical use case where you want to understand the data and understand the trend and analyze it and dig deeper into the data. So that kind of query use cases is called OLAP, whereas like the get, put, your like REST APIs that interact with the database, those are more OLTP transactions, right? Now Druid is designed for OLAP use cases. So it is heavily designed for OLAP kind of query workload. And there's so many different like storage systems and tools in the market these days. Probably, I wouldn't be lying if there was probably more than 100 like different kinds of storage systems. And where does Druid fit in this like very like diversified and very crowded world? So Druid tries to carve its niche in between like time series database, data warehouse, and then search systems. So Druid's like niche is like somewhere in the middle, and Druid is designed for use cases that involve either like OLAP use cases, which are more like data warehouse kind of queries, time series queries, and also search queries on full text search. So that's Druid's niche, and all the design features are inspired from these particular different database types, which we'll see as we go deeper into the design features of the database. And I also want to say, feel free to interrupt me at any point. We don't have that big of a group right now, so we can take questions as I'm going through the presentation. Um, and I'll also stop to see if anybody has any comments or any questions. So before moving on to the use cases, does anybody have any like comments, questions? No? Okay, I'll move on. So what are the ideal use cases for Druid, right? There's a time component to the data. Data is actually partitioned by time in Druid, and it's used for OLAP, analytics, slicing and dicing of data in many different ways. Updates to existing data are less common. So in Druid, you can't actually do an in-place update of a row, right? Normally in a SQL database, you'd be able to say, okay, update row with ID 1 and change the name from John to Mary, right? You can't do those sorts of things in Druid. The only way to update data is by re-ingesting the data set completely. So it's more attuned for things that are data sets that are more fact heavy. So what I mean by fact heavy is, let's say, clickstream data, right? Data around like user behavior. User A, Abhishek clicked this button, add to cart button, right? Usually what happens is an event gets created on that action, and that's a fact in a sense that Abhishek clicked this button at a particular point in time, right? That doesn't change, that doesn't update necessarily. So that's a fact versus what a dimension might be is at the point I made the click, I was living in New York, right? So that's a dimension on the fact, on the row. Address might be a dimension. There might be profiles like this. So basically you can have like facts and lots of dimensions in Druid, and Druid supports even up to like hundreds and thousands of dimensions. So you can slice and dice the data across different dimensions and do your analysis. And then Druid also has like real-time ingest aggregations and approximations, which we'll go into a little deeper later in the slides. And the biggest use case so far we've seen for Druid is actually powering GUIs of analytical applications. So I'll give you an example here. So an application like this, where you can like maybe go into the different dimensions, look at the graphs, see the trends. This kind of application is powered, is kind of use case is what Druid is really built for, where you're building an analytics UI, but the underlying data is actually being powered by Druid. So let me go into the key design features of the database. First, feature of first key feature that we're going to go into is column oriented. So this relates to the OLAP nature of queries in Druid, right? So databases, when you think of databases and how they are stored, like the actual records they are stored, right? We have a table abstraction in a sense that, hey, like we know a table and table has like many rows and columns, but this is actually not how data is actually stored in disk, right? It's not stored in this table representation like we are used to thinking of. It's actually stored in blocks, right? Blocks of bytes. Um, and so there's a row-oriented and column-oriented. So this picture here is how a table might be represented in a row-oriented manner, stored in a disk. So as you can see here, all the columns of the row are grouped together, right? Similar to how it would be in a table, right? And there's some sort of delimiter here that says, hey, like next row is coming in. One block can have many different rows in it, right? And then maybe there is one block that doesn't even have a complete row because the row itself is so heavy in data. So that's also possible. But the data is stored in a way that is the columns are grouped together. So this is in the row-oriented database, right? Now let's look at how the data is stored in a column-oriented database. So this is how it's stored. All the column data is stored together, right? So rather than this line by line, kind of like the entire row being stored together in one block, in one block of bytes, it's actually grouped by column. So this is the row ID column. This is the first name column, last name, and the social security number, and so on, right? So it's a different way of representing data. And now what I want to show you guys is a couple of queries and how we fetch data in a row-oriented design versus column-oriented storage design. So let's run some queries. A simple query, select first name from the table where the social security number is 666, right? Now we are going through the row-oriented storage, right? So what the database would do is scan the first row, first block, and then find that it's not there. Scan the second block, it's not there. Third block, 666 is there, and then return the result. But you only want to return the first name because it's only the first name that's requested. So you get DAR and you return it back to the caller. Now, what has happened is even though it only was asking for the first name, database had to read the entire chunk, right? And it had to read the entire column of the previous block as well, which is inefficient. Now let's actually take a look at the same query on the column-oriented database, right? So select first name from employee where social security number is 666, same query. Now database knows that we are filtering on social security number, so it can go directly to this to the byte block that has the social security number, right? So it can go directly into this thing, this byte block, because this is the byte block for social security number. Reads the first block, it's not there. Reads the second block, it finds it. And then the second, when it finds it, it also has references um, to the row, to the actual row. So there's like a reference ID 1006. So the database can directly access this particular byte block and then read only the first name because it knows that we're only asking for first name. So we don't have to actually go ahead and read other columns. We can directly go to the first name column and actually directly go to the specific block itself because the select gives us the reference to the record that we are trying to look at. So the idea behind this row and column oriented storage design is that in column oriented, when you're selecting specific columns, it's much quicker because you don't have to actually read extra data. And filtering is also pretty good because you can directly go to the column where things are being filtered on. Now, a little bit of a disclaimer here. Now, in the row-oriented example, databases these days use all sorts of tricks like indexing and multi-threading and whatnot to like make things faster. So whatever I explained was a little bit trivial and it was like a lot of things were assumed. In reality, it's not as simple as this. It's a lot more complicated. But the gist of the overall idea is that the way you group the data in the disk can affect how you what the cost of the query is going to be, right? That's the main idea, I think. Now let's look at an aggregation query. This is where a column-oriented database like really shines. So let's say select some salary from employee, right? So we're summing up all salary of all employees. What does the database do? The database can directly go to the salary column and just like sum all of the numbers and return back to the requester. Now imagine doing a similar thing in the row-oriented design, right? What the database had to do is read all of this data, but only get the salary and then keep adding up as it reads through the entire block of the database. So Druid, going back to Druid is a column-oriented design, and it's because it wants to support these like OLAP kind of queries that do a lot of like aggregations, group by, summations, filtering, compared to a, let's say, OLTP database, which would probably be row-oriented, right? So if you, in the row-oriented database, if you wanted to insert one new column, all you had to do is go ahead here and add another like row, right? And you're done. Whereas if you want to insert a new column in a column-oriented design, it's going to be a lot of work because you have to pretty much add one attribute in each block here, right? So updates are super expensive in a column-oriented design, and that's part of the reason why Druid actually does not support it. Whereas row is good for transactional workload, and column-oriented is good for OLAP kind of workload. So that's the column-oriented design choice, which makes sure that Druid is a good database for OLAP kind of use cases. Now we're going to be moving on to the time-based partitioning. Druid also partitions by time, and this is a feature that this feature in Druid is inspired from time series databases. So what does this provide us? So when data is partitioned by time, it means that range queries that are time-based become super fast, right? Analytics usually has a time dimension to it, in a sense that, hey, find me all sales that happened in the last year, roll them up and group them by customer type and give me the top 10, right? So it's there's usually a time dimension for analytical queries, and Druid actually partitions its segments. So segments are how like segment is Druid's native like file format that it uses to store data. Data in Druid is stored in segments, and then these segments are then partitioned across time. So all records from January 1st, 2000 to January 2nd, 2001 live in this area, right? All records from 2nd to 3rd live in these two segments, right? And all records from 3 to 4 live in this particular segment. So what this does is when the query analyzer analyzes the query, right? It can depending on the range that is provided in the query, it can directly find out which partition to work at, right? So if we wanted to search for, hey, what happened with all the sales yesterday? We don't have to read this partition. We don't have to read this partition. We know that we can read only the partition in, assuming that now was January 2nd. That is, we can only read at yesterday's like partitions, right? Segments here. So that way, when you're partitioning by time, the range queries based on time also become a lot quicker because you can rule out a lot of segments and not even query them. So that is another design choice that Druid has made, which ensures that time-based range queries perform a lot faster. Another key design feature that Druid has is inverted indexes for fast full text search. So this, Pramod has a question.
Yeah, so for the time-based partitioning, is this a unique kind of feature because it seems like any kind of database or any kind of data storage could store things like this, right?
Yeah, technically, yes. If you create an index on the time field, like you'd probably achieve a similar kind of query, like optimization on the query. Um, I think what is more unique is in a sense that Druid, like time-based partitioning is default in Druid in a sense that you can't actually ingest data that doesn't have a time dimension in Druid. So I think it's like more of a first class citizen in Druid compared to, hey, if you want to do these sorts of things in other databases, you might have to create your own indexes and things like that. Whereas in Druid, it's just like made and architected for these kind of use cases. I don't know the details of how they might be different. Maybe the other databases will just do indexing on time, will be able to achieve similar performance to Druid's like very customized design for time partitioning that I don't have knowledge about. So um, the only difference that I see is in Druid, it's more like first class, whereas in other databases, non-time series databases, it's more of like you have to kind of design or index the databases to uh, have it work that way.
I see.
Yes, another question.
Yeah,
Session.
I was kind of wondering, like, are the segments and partitions something that you would define, or okay, okay, that
Yeah,
makes sense.
yes, exactly. I will show you like a ingestion spec later in the presentation, and um, there's like a couple of attributes there which you can use to define these like this is called like segment granularity. So that's what defines the chunk timelines, right? That's what defines the chunk timeline. Yeah, we'll come there in the ingestion part of the presentation. Inverted indexes for fast full text search. This idea is derived from search systems like using Elasticsearch. The time-based partitioning idea was derived from time series databases. So this one's from the full index search. What is inverted indexes? It's very simple. It's just creating an index of the individual words to the particular. Here we are saying I copied this table from a article, which was more on Elasticsearch. So it's writes document, but in Druid it's segments, right? So segment one, segment two, in a sense that. So if somebody goes ahead and searches for pasta recipe, then what's going to happen is Druid knows that, hey, it's like segment one and segment two that is the result for this full text search. So that way Druid can provide a very quick result for full text search functionality as well. And these kinds of concepts come from search systems like Elasticsearch we've seen. Now I'm gonna go a little bit deeper into the ingestion side of things. Druid has a robust set of ingestion features. I think ingestion features in Druid really differentiate it from other databases. So let's dig into that a little bit more. What is ingestion, right? Let's first start with that. Database doesn't just live by itself. You need to put data into the database. So that's what ingestion is. Ingestion is a process that loads data into the database, right? And what happens in Druid ingestion? So in Druid ingestion, there's this component called middle manager, also known as the indexer, which is responsible for taking in raw data, either in a streaming format or a batch, not format, either in a streaming workload or a batch workload. And it's going to index the raw data and then output Druid segments, right? So it's ingesting raw data and outputting Druid segments, which are optimized for read. And let me go a little bit, explain a little bit about what is streaming and what is batch. Streaming pretty much means that it's an unbounded data set. That data is constantly coming. There's a more real-time aspect to it. Whereas batch means more data is bounded. It's limited how much, we know how much we're processing. Some examples of batch are like MapReduce and ETL workload, extract, transform, load kind of workload. They're like batch processing, whereas some messaging, distributed messaging is more on like streaming, such as technologies such as Apache Kafka, or distributed messages like SQS and RabbitMQ, I think is pretty popular these days. So those sorts of like distributed messaging systems are usually used for streaming ingestion, whereas batch involves like MapReduce, Hadoop, like ETL workloads as well. So middle manager is the component that converts the raw data into Druid segments. Now, there are many options of ingesting data into Druid. So this screenshot is from the Druid console. You can ingest from Kafka, Kinesis, Azure Event Hub. You can directly load from S3 as well, or other data lakes like in Google Cloud Storage, Azure, or just from an HTTPS endpoint, local disk, or you can reindex from Druid itself, right? You can use data as a Druid itself as a data source and re-index your data in a different manner than what it was indexed previously. So there's many different ways of ingesting data, and it integrates very well to whatever is the wherever you use your data, wherever you put your data. So ingesting data into Druid, they've made it very easy. Now let's go into ingest time aggregations and pre-computations. Now, at ingest time, users have an ability to aggregate data or do some computations on the data as well, right? So Simant, Sisam, you were saying, is that the segment granularity, the time chunk, is it configurable? Yes, it is configurable, and this is the attribute that controls it, segment granularity. So if you set it to a day, then the time chunk is going to be a day. If you set it to a week, it's going to be a week, month. And the idea behind what is the right segment granularity to put for your data set is something that you need to decide as a systems architect, depending on the data you have, right? Druid works best when segment sizes are like either 5 million rows or like up to I forget the exact like MB amount, but the ideal segment size is 5 million. That's the sweet spot that you want to hit, and you might want to experiment a little bit with the segment granularities to see what works best for the kind of data that you have. Pramod.
Just a quick question. So about that, like, can you not configure it by that? You know that that's the ideal size, right? Let's say that once the size hits that much, then you start a new segment, something like that.
I see. Yes, that is possible in batch mode ingestion, right? So in Druid, when you're ingesting data in batch, you already know all the data that is coming in, right? So what Druid has a native batch ingestion process, and what it does is it actually reads the data completely, creates a histogram of like the data, and then it actually creates optimized segments based on certain like parameters you put in the ingestion config, right? So later on in the demo, you'll see that there's ingestion configuration on, hey, how many rows to create in this segment, right? You can actually specify it over here. For batch, it works, right? But for streaming, data is gonna can come out of order. We don't know how much data is coming, right? So in streaming, it's not possible to completely optimize the segment size. However, there is a way to do it. You ingest through streaming once, and then you re-index the segments again based on batch, right? So when you're ingesting in streaming, you might not be creating segment sizes with optimal number of rows, right? But then once you have created those segments, and segments in Druid are immutable, they can't be changed. You can basically re-index those segments to make it more optimized on the number of rows. So that is something that the user can actually do. Does that answer your question?
Yeah, more or less. I was thinking something like when you ingest every piece of data, you can probably kind of read the size of the segment currently, right?
When you read a piece of data, you know the size of the segment currently. Uh, yes, you know the size of the segment. So let's say, for example, you have a row coming in, right? Segments are immutable in Druid, so you can't actually modify an existing segment that has already been published. So when a new row comes in through a streaming ingestion, um, what happens is like, depending on the batch that the stream, like it is also a kind of batch in Druid. Like if so, for example, there are 1,000 rows coming in from Kafka, right? And based on this ingestion config, they might be rolled up into, let's say, 100 rows, right? And they'll be stored in a particular segment, right? Now, the existing segments, they are immutable. So you can't actually add things to existing segments to make it more optimized. What you can do is once you have created that unoptimized segment, along with the previous segment that is already created, you can reindex these two segments and then create a new segment that is more optimized. So since segments are immutable, you can't just like go ahead and attach a new row into an existing segment. You have to always create a segment.
I see. I see. Makes sense.
So let's look at this ingestion configuration. So as you can see here, this is how ingestion, particular ingestion can be configured. Now, let me give you an example with the raw data and aggregated data. So let's say this is the data that is coming in Apache Kafka. So as you can see, it's e-commerce kind of data with order ID, merchant ID, sales created at. Now, with this configuration, as you can see here, we have set up query granularity to 15 minutes, and we have set up rollup to true, and we've created 1 dimensions and 2 metrics, right? So what our indexer or middle manager is going to do is, let's look at order ID 1 and 2, right? They fall in the same 15-minute window, right? They're in the same 15-minute window from 8:30 to 8:45. And they have the same merchant ID, same dimension. So what the aggregator, what the indexer is going to do is actually going to roll up these two order ID 1 and 2 into a row of its own, right? So merchant ID 1, total sales 70, event count is 2. So this event count comes from here. So we're just counting the number of raw data used to create this rolled up record. And we're also actually summing the sales, total sales, right? So just with this like very simple ingestion config, you can actually do pretty interesting rollups, aggregations, transforms, filters in Apache Druid while you're ingesting data. Now, why would you want to aggregate data, right? Now, depends on your query patterns. For example, maybe your query pattern is such that you don't actually care about specific sales for a specific order, but you only care about sales at a 15-minute granularity, right? You don't need 1 minute granularity. For your use case, 15-minute granularity makes perfect sense. You don't need to actually have that specific low-level granularity. So you can just aggregate the data, and what do you get in return? You get you basically save up on storage cost. Previously, you would be storing 2 rows, but you are storing 1 row, right? And then what also happens is you're kind of already pre-computing the data, right? You're already pre-computing the data to match what your query use cases and query patterns might be, right? So if you had to do, say, okay, let me actually go ahead and get the sum of sales of merchant ID 1. Previously, we had to read this row and also read this row, so 1 and 2, to get that result, right? Now the database only has to go read this one particular thing and return the result. So your query becomes faster, you save up on storage cost as well, but it has to match your use case. It's a design choice, and on the flip side of it, what happens is you're losing the order ID, right? As you can see here, when the data gets aggregated, we're actually not saving order ID. So let's say if you were interested in finding out which were the 2 orders that made this aggregated row, it's not possible. So it's a kind of trade-off that you're making, but for many like analytical use cases, it works just fine. And even in the use case that we have at Shopify, we are actually achieving a 90% roll-up ratio, which means that if our data was 10 gigs, if our raw data was 10 gig, we're actually only, our aggregated data is just 1 gig, because our basically ingestion pattern was such that the records were very collapsible, aggregatable, right? So this can be pretty nifty tool. And another thing you can do is even from one raw source, you can actually create many different aggregated data, right? You can create one data that is rolled up by 15-minute, maybe another data that is rolled up by 30-minute, another data set that does some other computations. You can also hook in like approximation algorithms and data sketches. I don't know a whole lot on this area because we haven't had the use case to do so. But you can tag in like approximation algorithms in these metrics and get some sort of approximations on the comments, which is some people say that that's one of the big advantages of Druid as well, where you can pick and choose your approximation algorithm and just hook it up in your ingestion config. And you don't even have to write any code for this, right? This is all configuration. Druid has the code to process this configuration and create the segments that you want. So as a developer, yeah, although I like coding, this is something that is really easy and makes my life very, very simple as well. Moving on. Now let's go into the architecture of Druid a little bit. So as I mentioned earlier, Druid is a distributed system, and it has 3 major node types. One is the query node, another one is the data node, and then there's also the master node, right? And these nodes can be deployed differently in different boxes, or they can actually be deployed together in a single box as well, depending on what your workload is like and what your use cases is. So data node, so query node, let's start first with query node. Query node is responsible for processing the query request and returning the data to the client, right? So, and okay, let's first go into the data node. So data node is to ingest and search for data. So there's ingestion happening into the data nodes, but then queries are also coming to the data node, and data nodes have to actually search the segments and return the results back to the query node, right? So those are the 2 responsibilities of data node, ingestion and querying. And then there is deep storage. So deep storage is usually a cloud storage like GCS or S3, where which Druid uses to actually back up its segments. So even though segments are loaded in these data nodes, they're also stored in deep storage, so that if a node dies and if it has to replace, it actually takes the segments from deep storage and rebuilds itself. So these are the 3 like main like data node types or node types in Druid. Now let me walk through a query flow, and let's also walk through a data ingestion flow, right? So what happens in a query flow? A client sends a request, select, let's say, first name from employee takeover, SSN is 666, in our previous example. And then the query node, what it does, it actually analyzes the query, plans the query, and then at some point it's going to determine, okay, these are the segments that we need to query, and it's going to send the request to the data node, right? And in the data node, we have 2 different processes, actually. We have the middle manager and the historical. So middle manager is represented as indexer over here. And those 2 process nodes like process those query, find the results, and return it back to the query node, right? So that's the query side of things. Query comes from over here, gets distributed to all the data nodes and index middle manager nodes and historical nodes, and then gets collected back at the broker, right? It's a scatter gather kind of algorithm. First you scatter the request, and then you gather the data and you push it back to the client. Now let's look at the ingestion flow, right? So either stream data comes in, either batch data comes in, the indexer is going to actually create the Druid segments, and it's going to push into deep storage. And then historical is actually going to pull from deep storage and then load it into its disk so that it can serve the query. So normally how a segment lifecycle happens, a segment gets created here in the indexer. It gets pushed into drip storage, and then it ends up in historical. So all new segments come here, go down here, and then end up here. So that's the lifecycle of the segment in Apache Druid. So in previous slides, I've mentioned the real-time aspect of Apache Druid as well. So what real-time actually means is even before the indexer creates those segments, data is actually already queryable, right? So as soon as, let's say, we're using streaming data and a new record appears in the stream, and then what happens is data is instantly queryable from the middle manager until even the point when the segment is created and then it gets pushed over to the historical. And at that point, the data, the result for that data is not going to be served by the indexer, but it's going to be served by the historical. So at one point, all data is actually served by the indexer until it gets pushed into dip storage and gets loaded in historical. So what that means is as soon as the data appears in the stream, it's immediately queryable, even though it's not in the appropriate Druid segment already. And there might be a bit of like increase in query latency because of that. But I don't have a lot of information of like how much of that cost there is. But it's a big game changer in a sense that, hey, like you want sub-second latency on data freshness, right? If you have that kind of use case, as soon as data appears on your stream, it's available for querying, which is one of the big advantages of Druid over some other databases where they require a little bit of time to basically produce the data in appropriate format. Now I'm going to go through a quick demo. If we have time, that is, I don't know how much time we have. We have only 10 minutes left. Should we go into the demo, or what do people think? Should be a quick one. Okay.
Let's do a demo, I think, right?
Pardon me?
Yeah, let's do the demo.
Okay.
And then we can have last 5 minutes to discuss.
Okay, sounds good. So here I have Druid. Yep. So I have Apache Druid running locally. Can you see my screen, by the way? Okay, good. And this is very easy to set up. You just go to the Druid website and download the library and just run it. It literally takes 5 minutes to set up. And you can load data, right? So you've seen this picture. This is where I like screenshotted the picture from. And I also have Apache Kafka running locally on my computer, right? So I have, can you see my terminal right now? Okay, good. So I have Apache Kafka running, and so I can create topics as well, right? So what I'm gonna do is I'm gonna ingest this data. So this is, I think, Wikipedia comments data, right? And what I'm gonna do is I'm gonna push this data into Apache Kafka, and then create an ingest in Druid to pull that data into Druid from Apache Kafka, right? So the first thing I'm gonna do is to create a topic. So let's say it's Wikipedia v2. So this is on Kafka. So let me run that, and fingers crossed it's gonna work. All right, so it says created topic Wikipedia v2, right? So we have a topic in Apache Kafka. So now what do? We post data into that topic, right? So there's this another script that is available in the Kafka package, which basically is outputting data into the topic. So I think the topic was Wikipedia v2. So let me go ahead and do that. Oh, not that. V2. Okay. Topic is Wikipedia v2. So what this is going to do is this is actually going to write the data into the Kafka topic. Let's see.
I think there might have been a symbol that you missed.
Did I? Oh, yeah, I missed the caret. Yeah, it needs to have that caret. Okay, there you go. P2. Yep, now it seems to be working. Let's wait for a bit. Yep, so it's writing the data, right? So we wrote the data. So let's go back to Druid. So Apache Kafka, connect data. So Kafka is running in localhost 9092, I believe. And the topic we created was Wikipedia v2, right? So we are data sampling from the start of the screen. So supply, voila, there's all the data, right? So we can parse the data next. So all Druid needs to have so this is the parse data. So Druid automatically parses it as JSON. Now next thing, we can actually, so it finds out the time column from the time ISO column in the data, in the raw data. And that's what it's going to use to index the data by the time column. You always have to have a timestamp column in Druid, or you can have Druid just assume a timestamp as well. So if your data does not have a timestamp, you can just assume one particular timestamp. That works too. Let's go to transform. So if you wanted to transform some data, let's say we wanted to concatenate, I don't know, delta and is anonymous, then we can do that as well. So it would be 36 false, this concatenating data if we wanted to. There are many different transforms that Druid supports. We can also do filtering. So let's say you want to filter data for a particular city name, Auburn, then you can do so. And then we can also configure the schema. So we can specify specific types on the column. And then we can also see if we want to roll up the data. For this one, since we don't have a lot of data, I'm going to disable the roll up. And then we can also specify the query granularity. So in the spec that I showed, query granularity was 15 minutes. But since we're not doing any roll up, the query granularity does not matter as much. And we can also add dimensions, add metrics like long sum, double sum, add like different sketches like approximation algorithms. And then this is the partitioning. So you can see like how many rows per segment you want to actually have. So I think ideal is like 5 million rows per segment. That's the sweet spot. Sorry, I think I saw it like 50,000 earlier. Yeah, it was supposed to be 5 million. That's the sweet spot for Druid. And then you can also specify segment granularity. So this is what controls the time chunking, like partition time chunking. And then you can specify so many different parameters. And one thing to specify is whether to use the earliest offset in Kafka or the latest offset. So let's use the earliest offset, and then go to publish, and you can edit spec. So this is what it creates in the end, right? You don't have to go through the UI particularly. You can just go ahead and create this JSON file. And all that the UI is doing is actually building this configuration, right? Now we can go ahead and submit. So our topic is this, our data source. So yeah, our data source is also Wikipedia v2. So data source is analogous to tables in MySQL, in SQL. So what is table in MySQL is actually data sources in Druid. They are not exactly like tables, but they behave like the overall abstract concept is very similar. So it's pending, now it's running, so we can go to query. So Wikipedia v2, right? Wikipedia v2 is not found yet, so maybe it hasn't loaded yet. Let's see. Ingestion, running, query. Yeah, usually these things happen. So v1 was running, but for some reason v2 is not running. Oh, v2, there you go. There it is. Yay. So you can see the data ingested into Druid. That's it for the demo. Now let me go back to the presentation. Just to recap, we had an introduction to Druid. It's a, real-time analytics databases optimized for OLAP kind of use cases. And then we also looked at different use cases that it's optimized for and different design choices that is made in Druid to basically fulfill those use cases. We also took a look into the architecture of the database, and we did a quick demo. So that's the recap of the talk. Now I want to actually end by sharing a bit of learnings. One of the best, not best probably, one of the more important skills I think as a software developer is to choosing the right tool for the right use case. These days with open source technologies, there's like so many different options that are out there. And I think one of the critical skills of a software developer is to understand the use case and pick the right tool for it. That's been a learning throughout my career, and I wanted to share it with you folks as well. Another is standing on the shoulders of giants. As you noticed in Druid, it basically draws inspiration from so many other data systems that has come before it, right? There's the there's the full text search, inverted index, which come from full text search systems like Lucene and Elasticsearch. There's the time-based partitioning, which comes from time series databases. There's also, what else is there? The column-oriented design, which is coming from data warehouse. So usually these all tools are like built, it's more like composition of existing innovations, and they build their own innovation on top of the existing innovation, which I find to be very nifty. And then power of open source collaboration and long-term consistent work. Druid was actually started in 2011, so it's been about 10 years, and it's open sourced. I don't think in any other industry you have this level of like mass scale collaboration on a volunteer basis. Maybe organized religion, but that's something amazing about software that just continues to bewilder me, and it's quite an amazing achievement, I think, of human beings just to be able to collaborate in such a large scale and volunteer time without anything in return. So that is something that is, I don't know, I appreciate that aspect of open source collaboration. And finally, I want to end on a bit of note about uncovering abstractions and picking under the hood. I had worked as a software engineer, or I've been working as a software engineer for 6 years. And I've used many different data systems, but they've always been a black box to me, in the sense that, hey, I use the APIs, I just get the work done and move on to whatever is next. Whereas this was the first time that I got to basically shed a light into the black box and see like what's going on inside. So taking time to go a little bit deep into a topic and understanding it from the ground up was a very fun and rewarding experience for me. So I would encourage you in your endeavors to also maybe pick a particular abstraction that you don't know very well and uncover it and see how it's like made on the inside. It's a lot of fun. I enjoyed a lot learning about these systems, and of course sharing it with you all as well. So if you want to get involved in the Druid community, it's open source. If you want to be a contributor or contribute in any way, you can go to the Druid Docs, and there's a lot of good information there about Druid as well. And if you want to contribute, you can go there and see how you can contribute as well. That's it for me. I know I've been talking a lot, and we went a little bit over time. So thank you for listening. You've been a great audience. Cool. And now let's open it up for discussions and questions. I know we are a little out of time, but if people have any questions, I'm more than happy to take them.
I have one. So 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 you mentioned that there's this notion of query node and the data nodes, right? So
Mm-hmm.
when you set it up and when you want to scale this out, right? There's this
Yeah.
question: how much of your compute resources you want to allocate to query node versus the data node? Is that something you have to specify as a developer, or is that taken care of by the cluster management system?
Yeah, so Druid, you have to set up the cluster yourself right now. There are companies that provide like a managed Druid resource as well, similar to how AWS manages DynamoDB for us, right? Uh, and we don't have to worry about setting up the cluster and anything like that. There are companies like Imply that actually provide that kind of experience for Druid, but it's on a paid model. In Shopify, where we use Druid, we actually have a infrastructure team that is dedicated to set up clusters and hardware. So they actually, what they do is they build the cluster from scratch using, we use Google Cloud, so we use Terraform, which is like a cloud formation kind of thing. So they build all these clusters and they specify how much resource to use for what kind of data node and or master node, query node. In our particular use case at Shopify, at least the project that I'm working on, our streaming workload is a lot higher than our query workload. So we actually have much beefier middle managers and historicals than our query node is just like a 3 or 4 hosts. So that's one of the advantages of having a distributed system, is that you can scale them in different ways depending on your workload.
Yeah, Binit has a comment for you, Abhishek.
Let me see. How do I see the comment?
Okay. So Binit,
Chat. There you go. Okay. Yes. Thank you so much. The column is very interesting. I wanted to learn more. I like the categorization of Druid. Cool. Yeah. Thank you. Yeah. If you want to learn more about it, actually, if you noticed in my slides, I've referenced some sources here, and I have shamelessly copied slides from a YouTube video for these particular ones. So as you have noticed here, there's a pointer as well. Like, some of them have like a pointer. Yeah, I can see here. There's a pointer here. So I've copied them. So I'll be sharing the slides. So if you go to this YouTube video, there's a much detailed explanation of the column and row oriented databases. And yeah, thank you for joining in. I really appreciate your time and attention.
all right. Yeah, I think that's gonna be it for today. We are over time 5 minutes, but thank you guys so much for joining again, and we'll see you next month. Maybe earlier than that if we do the networking event.
Thank you.
All right. Bye bye.
All right. Bye bye, everybody.
Bye.